So we're now going to have a look at what happens in the atmosphere much more closely. We're going to look at our weather. To begin that exploration, we're going to look at one of the main features that you see every day outside when you're looking at the weather, and that's wind. Why does air move? What causes the wind to blow? It's not the fluffy white clouds that cause wind to blow. There are three forces acting on air particles in our atmosphere that cause them to move. The first is known as pressure gradient force. The second is Coriolis force, or the Coriolis Effect. And the third is friction. All right, let's work with the first one. Let's have a look at what pressure gradient force is. Now, you've seen this diagram before. We looked at this diagram when we were having a look at differential heating on the Earth's surface. Why does land heat up more than water does? Because it was due to the specific heat capacity differences, the differences in transparency, the differences in turbulence, the differences in latent heat of evaporation. Now, we can use this diagram to look at pressure gradient force. It's a localized example of what pressure gradient force is, but it's nonetheless a useful place to start. It also is what gives us a sea breeze. Have you ever noticed when you go down to the beach that it's always windier down at the beach, usually, always windier than if you'd come in from inland a little bit. And the wind seems to be blowing in a particular direction. It seems to be coming off the ocean, and so sometimes makes it feel a bit cooler than it was when you left home if you live 30 kilometres inland. So in looking at pressure gradient force, it'll also help us to explain what a sea breeze is. Now, we know that land heats up more quickly than the ocean does. And as what's going to happen to the air that's closest to the land surface? Well, it's going to heat up as well. Remember, we learnt that the atmosphere doesn't heat up from the incoming solar radiation. It heats up from the long wave radiation emanating from the Earth's surface. So the air closest to the Earth's surface will heat up, and it'll become hotter than the air that's above it. And so what happens? Well, hot air will rise. So the air that's on the land surface will start to rise on a hot day. Now, if it rises, it's going to create a gap. As that air rises, it's going to create a gap underneath it. That needs to be filled from somewhere. Well, the place it's going to come from is going to be from the ocean. So the hot air on the land rises and the air is filled. That gap is filled by air from the ocean. There is our sea breeze. Okay, hot air rises, creates a gap. Air has to come in from somewhere. Cooler air from the ocean comes in to fill that gap. Once that happens, then it can heat up as well, and it too will start to rise. And it'll keep rising until it gets to a point where it starts to cool and can no longer rise and will start to fall back down. Now, as that air starts to fall back down, there's still air moving in because there's still air rising, and you get this convection cell developing, where you've got cooler air coming in from the ocean, your sea breeze, heating up on the land, cooling, moving out, starting to fall back down onto the ocean. Now, when that happens, we have a pressure gradient difference. Because as that air rises and moves out, that means you've got less air above. You would have less air above you if you were standing on the land surface compared to if you were out in the ocean where all that air was starting to fall back on you. Now, of course, you can't tell that. You can't feel that difference usually. Some people think they can. It gives them headaches and so forth. But generally, you need instruments in order to measure the amount of air that's above you. The more air that is above you, the greater the pressure on you. The less air that's above you, the less pressure you have. And so this effect of low air pressure on the Earth's surface and high air pressure on the ocean means you have a pressure difference. And so what is actually occurring there, because of this difference in pressure, is that you've got air moving from areas of high pressure to areas of low pressure. And that is one of the fundamental reasons why air moves. It always moves from areas of high pressure to areas of low pressure. And the speed at which air moves is dependent upon the difference in that pressure gradient. So if you've got a very large difference, so you've got very high air pressure somewhere and a very low air pressure somewhere, then that gradient will move much more quickly. And it's very similar to steep areas on a topographic map, which you've all looked at now. So if you've got an area of high elevation and an area of low elevation, very low elevation, and they're quite close to each other, then you have a very steep area, and if you had a ball and it was flat, you could roll that ball really quickly down that slope. So that's not a pressure gradient difference, that's an elevation gradient difference. And where have you seen these sorts of lines, like topographic lines on a map? Well, if you watch the news every night, usually most news broadcasts, at the end will have the weather report. And you've seen these synoptic charts. Those lines on the map are just lines joining up areas of equal pressure. Just like on your topographic maps, you saw those contour lines that were lines joining up areas of equal elevation. An isobar or an isoheight, as they're now called, are just lines joining areas of equal pressure. And we'll look at these in much more detail. Okay, so what a bit later on. So what these maps are also showing you is that it's not just a simple air moving only from areas of high pressure to low pressure. There are other things acting upon that air to make them move in different ways. That's what those two other forces are. Okay, so the second one we're going to look at is called the Coriolis Force or the Coriolis Effect. Now, this can get very, very complicated. And if you do a Google search online, you will see there are dozens of videos about the Coriolis Effect. Most of them involve people throwing balls or watermelons or people on swings and roundabouts. And I've been to them all. And look, I think I've found one of the ones that is the simplest. It is clear, and I think is the most useful. So rather than me rabbiting on, I'm actually going to play this video because it really does show it what the Coriolis effect is really well. So let's watch that now.
The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection. As the atmosphere rotates with the Earth, it is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and has moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere.
Okay, so putting it very simply, you have a look at this diagram, which is very, very old. I've been using this for many years. But very simply, the Coriolis force causes air to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. Now, eventually, over time, what that means over a short period of time, as that air is moving, somebody on the Earth's surface, it will look as though the wind is moving directly to the east or directly to the west along those isobars. Okay, so you've got your pressure differences. It will eventually look as though if only pressure gradient force and Coriolis effect were in operation, then all winds would just move directly along those isobars in easterly or westerly direction. But it doesn't. And so the final force is friction. And so what happens is, because the Earth's surface is rough, and there are differences, it's rougher on the land than it is on water, but nonetheless, water still has friction.
So the effect of friction is to reduce the deflection caused by Coriolis. Without friction, such as in the upper atmosphere where friction is negligible, as we've seen before, Coriolis and combined with the pressure gradient force would mean that the wind would move eventually parallel to the isobars. But with friction, it reduces the deflection effect of Coriolis, so it doesn't quite bend as far as would be predicted without friction. So if we have a look at this high pressure cell, the red line is the pressure gradient force, the black line is Coriolis deflecting the air to the right in the northern hemisphere, and the blue line is friction. And you can see there the net effect is, as air moves out of the high pressure cell, it moves towards the low pressure cell in a clockwise direction in the northern hemisphere this time. Okay. If we have a look at a low pressure cell, then as air moves in following the pressure gradient, the red line, it wants to move into the low pressure system. But again, because we're in the northern hemisphere, Coriolis wants to deflect it to the right, but friction will slow down that effect. So the net effect is that the air does make it towards the center of that low pressure cell, in this time in an anti-clockwise direction. Again, in the northern hemisphere, in the southern hemisphere, the directions would be different.
All right, so that's why wind moves and why we get those particular patterns we see on the weather report each night.